Deep beneath the flat plains of Kansas, a quiet revolution in nuclear energy is taking shape. On December 9, 2025, Deep Fission officially broke ground on what is being called the world's deepest reactor in Parsons, Kansas. At first glance, it sounds like science fiction, a nuclear reactor buried 1 mile underground. But this project isn't about theatrics. It's about solving some of the hardest problems in energy: safety, scale, and delivering power to the places that need it most. The concept behind Deep Fission's borehole reactor is radical yet elegant. Instead of building towering above-ground facilities, the reactor will be constructed in a vertical shaft drilled a mile deep into the earth. This subterranean approach provides natural shielding from radiation, dramatically reduces the need for complex containment structures, and leverages the surrounding geology for passive cooling. Essentially, the planet itself becomes part of the reactor's safety and operational infrastructure. This isn't just a theoretical exercise. Deep Fission's Parsons site represents a pilot project, the first step toward a much larger ambition. Their strategy revolves around modular, scalable borehole reactors that can be replicated across multiple sites. By going underground, they reduce surface risk, minimize land usage, and address one of nuclear energy's biggest public perception challenges: safety. For communities wary of traditional reactors, a mile-deep installation is both reassuring and practical. But safety is just the beginning. Deep Fission is already thinking like a utility of the future. The company has reportedly secured a pipeline of letters of intent totaling 12.5 GW with AI data centers, signaling a new kind of customer for nuclear power. Data centers are voracious consumers of reliable 24/7 electricity. Their operations cannot tolerate grid instability, and renewable sources alone often can't guarantee the consistency. Deep Fission's borehole reactors are designed to fill this gap, delivering constant, carbon-free power to facilities that demand reliability above all else. The underground design has multiple technical advantages. By building vertically, the company reduces the complexity of heat management. Gravity and natural rock conduction assist in cooling, and the depth provides additional pressure containment, which simplifies reactor engineering. Components can be modularized and lowered into the borehole sequentially, allowing for phased assembly and easier maintenance cycles compared to traditional reactor construction. Deep Fission's pilot reactor in Parsons is more than a single experiment. It's a proving ground for a potentially global energy model. If successful, these deep borehole reactors could be deployed in regions where surface space is limited, population density is high, or safety concerns make conventional reactors politically unfeasible. By burying the reactor, the company essentially creates a self-contained nuclear system, isolated from the risks of weather, accidents, or surface-level human activity. The timeline is ambitious. While a mile-deep reactor presents enormous engineering challenges, the company's phased approach, starting with a pilot unit, allows them to refine the technology, demonstrate operational safety, and build credibility with regulators and investors. This is a critical step because nuclear projects live or die on their ability to navigate regulatory approval. Deep Fission's underground approach may streamline certain safety certifications while adding new complexities for geotechnical assessment. One of the most interesting angles of this project is its alignment with AI infrastructure. Data centers are increasingly looking for on-demand, carbon-free power solutions. Solar and wind can't reliably deliver continuous, high-capacity electricity, and traditional reactors are slow to deploy. Deep Fission's underground modular reactors could offer AI companies a near-instant solution to scale their operations sustainably. The 12.5 GW in letters of intent isn't just impressive. It signals a market-driven validation of this unique approach. From a financial perspective, The Parsons groundbreaking and the subsequent pilot deployment show that investors are willing to fund truly innovative nuclear strategies. Unlike surface reactors that compete for land, permits, and public approval, the underground model could accelerate deployment timelines while offering enhanced safety and lower operational risk. That combination is compelling in an industry historically burdened by skepticism and delay. The borehole method also introduces operational efficiency. Modular components can be pre-tested above ground, then lowered into the shaft and connected systematically. This reduces assembly errors and allows for rigorous quality control at each stage. Traditional nuclear construction suffers from on-site customization and iterative adjustments, often leading to multi-year delays. Deep Fission's strategy seeks to eliminate these inefficiencies by turning reactor construction into a precisely orchestrated industrial process. Another advantage of burying reactors underground is resilience. Surface infrastructure is vulnerable to weather events, natural disasters, or even targeted attacks. A mile-deep installation inherently mitigates these risks, offering not just safety from radiation, but security and reliability. For high-value customers like AI data centers, that added layer of resilience is extremely attractive. It's also worth noting the symbolism of Kansas in this story. Traditionally, the state isn't associated with cutting-edge nuclear research, but Deep Fission has chosen Parsons for its geology, regulatory environment, and access to critical infrastructure. This highlights a growing trend. Innovative energy solutions are no longer confined to coasts or tech hubs. The energy revolution is happening where conditions are right, not just where headlines are made. For the broader nuclear industry, Deep Fission's strategy could be transformative. By demonstrating that reactors can be safely constructed underground using a modular approach, they may redefine public perception and regulatory pathways. Communities that were hesitant about traditional nuclear projects may be more receptive to borehole reactors, opening doors to deployment in previously off-limits areas. Of course, challenges remain. Drilling a mile into the earth, managing the unique thermal and structural loads at that depth, and integrating the reactor with grid infrastructure are non-trivial tasks. Delays and unexpected engineering hurdles are almost guaranteed, but the potential payoff, a safe, scalable, and reliable nuclear energy model that can meet the needs of modern, data-driven economies, is enormous. The Parsons groundbreaking is more than ceremonial. It represents the first tangible step toward operational underground nuclear reactors. Each cubic foot of excavated rock, each modular component lowered into the borehole, brings the vision of continuous, reliable, and carbon-free electricity closer to reality. Here's a question for you. When you think about the future of nuclear energy, do you picture towering cooling towers and massive surface plants? Or do you imagine discrete, underground installations powering the digital backbone of our economy? Deep Fission is betting on the latter, and their investors, their customers, and their engineers are all placing their faith in this unconventional vision. The scale of ambition is clear. With 12.5 GWh of preliminary commitments from AI data centers, Deep Fission is not just testing a concept, they're aiming for immediate commercial relevance. These early customers will be the proving ground, showing that underground reactors can provide both scale and reliability to industries that cannot tolerate downtime. In the months and years ahead, all eyes will be on Parsons. Will Deep Fission's mile-deep pilot reactor deliver on its promise? Can modular borehole reactors meet the rigorous standards of safety, efficiency, and reliability required for grid integration? The answers to these questions will shape the trajectory of not just this company, but the broader future of nuclear energy deployment. And here's something to really think about. If this model succeeds, the nuclear landscape could shift dramatically. Instead of massive above-ground projects requiring decades to build and navigate public opposition, we could see replicable underground modules quietly powering critical infrastructure across the country and the world. That's a paradigm shift in how we think about nuclear energy, risk, and industrial strategy. Deep Fission's Parsons project is bold, risky, and ambitious, the kind of initiative that could either redefine nuclear power or serve as a cautionary tale for what happens when physics meets logistical complexity. But the fact remains, a mile underground, the future of nuclear energy is literally being built. The next few years will reveal whether Deep Fission's borehole approach is the missing link between concept and reality. One thing is certain, the world is watching, and if successful, Parsons, Kansas won't just be a site on the map. It will be the blueprint for the next generation of nuclear energy.